once I have chosen one such thing out of these three possibilities, then I am left with two. That two is available for this place. And then once I have chosen out of those two, once I have chosen one, then I have only one possibility remaining. Now look at this. These three things, each one of them is giving me 2. 2, 2, 2. Now these two things, each one of them is giving me 1. Okay, A gives me T, T gives me A. It does not increase anymore. So if three things, each one of them is giving me 2, so together they will give me how many possibilities? 3 times 2 times 1 actually, but we can ignore that, and that is 6. See, this way we have to think of this number 6. Now you can see why we have 24 here. If I have 4 places for the letters of the word rose, right? So for the first box I have 4 possibilities, either R or O or S or E. R, O, S, E. Now once I have chosen R, say, then for the second box, don't say at once 6 here. Okay, that's the way we proceeded in the beginning. For R we have 6 ways, for O we have 6 ways, for S and E. Now we are trying to think of it in a more elementary manner. Once I have chosen R, then I am left with 3 more things. Out of those 3 things, so for this I have 3 possibilities. Out of these 3, once I choose something, then the second one, for the second one I have 2 possibilities left, and for the last one, not the second one from this way, first one, second one, third one and fourth one. For the fourth one I have only 1 possibility. So if I choose R and then O, then I can write S or E, or for this same thing I can write E or S. But this is not the only case. In place of O, I can have S or E, and for each such I will have 2. So 3 times 2. But that's not all. I can change R also. So for each such change I am getting 6. 3 times 2, 3 times 2, 3 times 2 and 3 times 2. 4 times 3 times 2. So that's why I get 24. 4 times 3 times 2 times 1 is equal to 24. So what we have understood here is that if you have m ways of doing something, listen to me carefully. If we have m, let me not use variables. If I have 4 ways of doing something, and for each of those 4 ways I have 3 ways of doing something else, then together I have 4 times 3 ways of doing both the things. Okay, and the reason we are multiplying this is apparent from this discussion, and this is called the multiplication rule or the fundamental rule of counting, and this we will be using all the time in solving this type of problems. Okay, so now we understand why the formula looks like this. It's because we have n places. N is any positive integer. For the first place you have n choices. Once one choice has been made, for that choice the second place has n minus 1 choices because one has already been made. So together the first and second place can be filled in n times n minus 1 ways. But then you have more places also, and as you make more choices, the number of available choices decreases one by one. So n times n minus 1, n minus 2 up to 3, 2 and 1. Okay. So now this is the starting point. We will now, okay, so what have we achieved? We now know that if we are given n distinct objects, the number of ways of arranging them along a line is this number. We have used mathematical induction to prove this, which is rather easy, not very difficult, but that does not give us any insight as to why the formula looks like this. That has to be seen using this fundamental principle of counting. Now next, we make the situation more complicated or worse. Okay, now suppose we have that same rows. Okay, so we have rows, we have 4 distinct objects. Now instead of trying to find out the number of ways of arranging all 4 of them, suppose I choose to have only 3 places. But the number of objects is 4. Now how many arrangements can I make? That is another question. Okay, it's not necessary that I have to take all of them. I may choose to take any number of them. So let us first go by brute force and try to write all of them. Now I can choose R, O and S. Okay, now R, O and S. We don't have to really write all of them. Instead, what we do, you already know how many possibilities you will get here. 6, because there are 3. Okay, 3 distinct objects. But instead of R, O, S, we can have R, S, E also. That will also give me 6 possibilities. Or we can have R, O, E. That also gives me 6 possibilities. Or we can have O, S, E. Okay, that also gives me 6 possibilities. Right? So in this case also we see, am I getting the correct thing? R, O, S, R, yes, because if I don't choose E, then I have R, O and S, and that gives me 6 possibilities. Like that I can remove one of them. So 4 times 6 is 24. Okay, so again we are getting 24. Right, again we are getting 24. Now if we use the principle of the fundamental principle of counting here, what should we get? For the first place, I have how many choices? 4 choices. R, O, S, E. 4. Once one choice has been made, the second place can be filled in 3 ways, because I have 3 of them left. Once that one such choice has also been made, then for the third place I have 2 ways. Since multiplication by 1 actually does not change the number, that's why I am getting 24. So in this case, the total number of possible arrangements is 4 times 3 times 2, which is also 24. Okay, incidentally, in this case also it's 24. But if I reduce the number of possible places, if instead of 3 places I now have 2, what will now happen? Okay, I can have R and O, O, R, or OS, SO, SE, sorry, ES, SE, RE, ER, and then let me write here RS, SR, OE, EO. If you observe this list, you will realize that we have actually written down all the possible arrangements. Now, here what is the number? Same, you just use fundamental principle of counting. For the first place, I have 4 possibilities, 4. For the second place, once a choice has been made for the first place, the remaining things give me 3 possibilities. So I have 4 times 3 different types of arrangements. 12, which is 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So now we understand that no matter how many distinct objects we are given and how many of them we can choose, we can use the principle of counting to easily find out the number of possible arrangements. Now this leads us to a generalization of that formula, n times n minus 1 all the way up to 1, 3 into 2 into 1. So the generalization is a result which looks like this. And now we don't have to use mathematical induction to prove it or anything, because we now know why it is true. Or I can write it as a result. I should actually use formal names like theorem or proposition, lemma, but anyway, what I call it really does not matter at this stage. Let's just call it a result. It starts off in the same way. Let n be a positive integer. Let R be a positive integer such that R is less than or equal to n. Okay, so we have 2 positive integers, n and r. R is not greater than n. R is either less than n or equal to n. The number of arrangements along a line that I think I can also write the number of linear arrangements, but I am not so sure about the terminology. Anyway, the number of arrangements of n distinct objects taking r at a time. This is important. We are not necessarily choosing all the objects. We are choosing r of the n objects, r at a time, along a line is n times n minus 1 times n minus 2, etc. up to n minus r plus 1. I have to explain why it looks like this. Okay. You see, you just proceed in the same way. You now have r places. This is place number 1, place number 2, this is place number, let me write one more, place number r minus 1 and then place number r. Okay. Now r can be either 1 or 2 or 3, and it can increase, it can be at most n, but it cannot be greater than n. Okay. Now same, you start applying the principle of counting. We have n distinct objects, so for the first box we have n choices. Same for the second box, once a choice has been made for the first box, the second box can be chosen in n minus 1 ways, or it can be given n minus 1 objects, any one of them. In this way, if you continue, you just have to understand what will appear here. You see, here we have n minus 0, here we have n minus 1. So when we have something here, we are subtracting from n 1 less than that thing. When we have 1 here, we are subtracting 0. When we have 2 here, we are subtracting 1. When we have r minus 1 here, we are subtracting r minus 2. Remember, subtracting r minus 2. Okay, so don't forget to put the bracket. And this gives me n minus r plus 2. That's why at first it looks a little confusing. When we have r here, we are subtracting 1 less, r minus 1. So this is n minus r plus 1. And you multiply them and you get this number. Right? So this is the beginning. Okay, I keep on saying this is the beginning because this is really the beginning. There are many more things here to consider. That is because we are so far considering only distinct objects. That will change soon. Now, using this understanding, this little understanding that we have had right now, let us try some problems. So there are, let me write down the questions. There are 4 flags of different colors. Okay, 4 flags of different colors. A signal can be sent. A signal can be sent by putting one flag above another. A signal can be sent by putting one flag above another. So how many possible signals can be sent? Okay. So we have 4 flags of different colors. A signal can be sent by putting one flag above another. How many possible signals can be sent? So what this says is that, say you have 4 flags, blue, green, of these colors, yellow and red. The colors don't matter, as you already know. The objects themselves, they don't matter. Their nature does not matter. Their number matters. So it looks like this, something like this. On a vertical pole, you can put them one above another. Say you put blue above green. That constitutes a signal. When someone looks at it, he or she will understand something. from a distance that something has to be done or it means something. Instead of this, if you have say yellow and blue, say, then that constitutes another signal. So we have to find out the number of possible signals. So you see, when you look at this problem, it's just simply asking you to find the number of ways of arranging 4 objects when we take only 2 at a time. Okay, one flag, another flag. Also note that they are of distinct colors. So that means they are distinct objects. So now the solution is quite simple. 4 times 3, because for the first one, instead of thinking it in a vertical fashion, you can think of it in our usual horizontal fashion also. For the first one or for the one on top, there are 4 choices. For each such choice, the one in the bottom can be chosen in 3 distinct ways. So together they can be chosen in 4 times 3 ways. So there are 12 possible arrangements of the flags. Hence there are 12 possible signals. For the solution, the things you have to write are quite easy. You have to write all the things and all the arguments. You have to properly logically write this is why, and then using the fundamental principle of counting, we get this number. So the technique is important. Okay, that's what we will do here. We will not write formal solutions. When we go to higher parts of mathematics, when things get more and more and more complicated, then we will write formal solutions, because otherwise you will quickly lose track of the things. And these situations are so easy, that's why I leave it to you. Okay, to tackle the next question, however, we should see something else. Let me first write down the question and then we will see what we need to tackle this question. If repetition is allowed, if something can be repeated, how many even numbers with 2 digits can be formed with what? With the numbers 1, 2, 3, 4, 5. Now this is a situation where what we have done so far is not enough. We have to look for new methods. You see, the case where we considered cat, there the objects were distinct, right? Now, objects were distinct, that is fine. But if we are told something like this, that you can fill in these boxes using these letters, but repetition is allowed. Okay. Previously, repetition was not allowed. We did not bring this point out at that time because we were starting. But now, if I can repeat a word, I can repeat a letter. First of all, you see, before you apply the principle of counting, you look at these boxes. Previously what we had three choices for the first box. Now also we have three choices. Previously, once we chose a letter, that cannot be chosen again. We were left with the remaining two letters. But now, since repetition is allowed, C can again occur. Okay? C can again occur. So, for the first box, I have three choices. But for the second box also, I have three choices. Why? I don't have two choices any longer. I still have three choices because C can again appear. Letters can be repeated, that is allowed. So 3, and again for the third one also I have 3. So in this case, instead of 6, I get more, namely 27 of them. Okay, instead of 20, okay, see, this has increased so much. It used to be 6, but since repetition is allowed, we now have 27. If you want, you can try to find them. They will look like this. Say you can have CCC, CCA, CAC, ACC, things like that. Okay, where only A and C are there. See, previously using only A and C, we were able to write down only 2 arrangements, but now we can write many. And also the arrangements that we wrote using A and C when without repetition were only AC and CA. But now you can, since repetition is allowed, you can have any number of places you wish. This is a situation where the number of places can be more than the number of available objects simply because repetition is allowed. That is the case here. So this sort of application of the principle of counting has to be used in solving this problem. So now what is said here? If repetition is allowed, how many even numbers with 2 digits can be formed with these digits? Okay, now 2-digit numbers. So I have 2 places. But keep in mind, the numbers have to be even. Now, and you may remember from your school days that a number is even if and only if the last digit of that number is even. So the last digit in this case can either be 2 or 4, because 1, 3 and 5 are odd. These are the available objects. Out of them we have to form the arrangements, or in other words the numbers in this case. So the last one can either be 2 or 4. So there are 2 choices for the last one. See, I have already said it need not start from this side. It can start from any side. Okay, as long as the counting is correct. So there are 2 choices for the last box, 2 and 4. And for the first box, you see, repetition is allowed. Okay, so for the first box, can I not have all of these? I can have, because if I have 2 here, no one is preventing me from writing 2 again here, because repetition is allowed. So I can write 2 here, I can write 4 also here, in spite of having say 4 here. That is allowed. But I cannot write say 2, 3. I cannot write, because this is not an even integer. This place should not have any odd digit. It can have either 2 or 4. So For this place I have 2 choices, for this place I have 5 choices. So together they give me 10 numbers. If we want, we can actually write those 10 numbers and see that they are really 10. Okay. Did I knock the camera? Let me just see. Now it's okay. So for this one, let us just quickly try to write all the numbers. If I have 2 here, I can write 1, 2, 2, 2, 3, 2, 4, 2, 5, 2. If I have 4 here, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4. So these are the 10 two-digit numbers that are even and that can be formed using these numbers. See, they are 10 in number. That's what we found. So this problem has also been solved where repetition is allowed. Okay, still the objects are distinct. Okay, in spite of having distinct objects, there is the case of having repetitions or not having repetitions. Next, let us take one more problem. Let us take this one. There are, again a flag problem, there are 5 flags of different colors. There are 5 flags of different colors. Any number of them can be arranged on a vertical pole to form a signal. So it's just like this one, except we have 5 flags, there were 4 flags, and now instead of having just 2 flags, one on top of another, we can have any number of such flags put in a vertical fashion on a pole to form a signal. How many different signals can be formed with at least 2 flags? Okay, so there is a restriction, although it seems like there is no restriction on the number of flags, but there is a restriction. There has to be at least 2 flags. So this does not constitute a signal. The pole by itself also does not constitute a signal. The signals start from here. It can be like this also, or 4 or 5, all of them. Okay? Now what to do in this case? See, in this case we have to handle the different cases separately. We have to find out how many arrangements or how many signals we can have with 2 flags, how many we can have with 3 flags, how many with 4 flags, and how many with 5 flags. And they have to be added. You see, this is one point where people get confused. We are speaking of the fundamental principle of counting where we are multiplying, but at the same time sometimes we are adding. See, multiplication is only there when the number of you do something in m ways, you do something else in n ways, and these two things are related, then only we multiply. You see, in this case where we have two flags, there we multiply the number of flags we can put in the top position, and the number of flags at the bottom we can put. Those two numbers we have to multiply. But these arrangements are not related to these arrangements. Okay, they are not related in the way that this signal is somehow affecting this signal. Any signal involving two flags is independent of any signal involving five flags, because you can see why they are independent. In counting the number of 5 flag arrangements, 2 flag arrangements are not used, they are not considered. So that's why there we don't need to multiply. Okay, so the number of signals with 2 flags is what we have two places, okay, two vertical places which can be written horizontally also. For the first place, I have 5 possibilities, I have 5 flags. Now once a flag has been chosen, you see nothing has been written about repetition, which means if nothing is given to you, you should assume that you cannot repeat. If something can be repeated, it will either be explicitly mentioned or the situation itself tells you that something can be repeated. Okay.